Hi and welcome everyone. I hope you're all doing well. We had a week's break from this seminar series and now we're back. So thank you to everyone for joining. We are very happy and excited to have Chris Knittel and Samuel Stolper giving their paper on using machine learning to target and extrapolate the case of household energy use. So Chris will be giving the talk today. Chris is the George Schultz Professor and Professor of Applied Economics at the MIT Sloan School of Management. Chris's work is generally in the areas of industrial organization, environmental and energy economics, and also applied econometrics. He's currently the Associate Editor of the AEJ Economic Policy, the Journal of Industrial Economics, and the Journal of Energy Markets. I'm very happy to have Chris today because this sort of his work and this paper is very close and dear to my heart. Chris's work has been some of the papers that I like from his is thinking about the regulation of transportation of energy markets and how we think companies, both utilities and car companies, respond to regulation and how that affects the fuel economy and how does that affect energy efficiency. But also his work is focused on thinking about how do we apply our sort of methods to understand the welfare effects of any policies in this area. So one of his recent papers in the JPE is extending the sufficient statistics approach to understand how do we capture the welfare effects of pricing policies that are used to address externalities. So in a sort of similar vein, today's paper is hopefully going to be on thinking about sort of a non-price intervention and how can we improve the efficacy and the welfare effects of such policies in the energy market. So thank you all for joining, and Chris, thank you for joining, and over to you.
Yeah, thanks Rob for that introduction. Thanks for having me and Sam. So Sam, as Rob mentioned, is on. He'll be manning the chat and Q&A if anyone has the tough questions. But I was telling Rob earlier that, hopefully this is more interactive than just me talking for 45 minutes. So if you have questions, comments, concerns, please put them either in the Q&A portion or raise your hand if that's an option. All right, so just a little bit of background on this paper. So this paper started, and I could still remember the lunch. Sam and I were sitting right next to the head of energy efficiency for Eversource at a research conference that my center runs twice a year. And he was talking about O-Power and how they leverage O-Power to meet certain demand reduction targets from regulators. And Sam and I started probing him on, who gets O-Power home energy reports and who doesn't. And, basically he said they send them to as many people as O-Power will let us. And I forget whether it was Sam or I, but it was probably me because it was an unfounded claim. One of us claimed that, we could do better than that. And if you gave us the data, we would be able to tell you who should be receiving O-Power home energy reports and who shouldn't be receiving O-Power energy reports. And then we went on to, start talking about how you might change what's inside those home energy reports to better target the intervention. So what it often doesn't work out this way, but then next week we started talking about data transfer agreements and so on. And ever since then, it feels like it was last year, but I think this was more like 4 years ago. We've been working pretty closely with Eversource on their behavioral nudges, they call them, and trying to optimize just not only who they send them to, but we're trying to get some new experiments off the ground that would change the messaging as well. So this paper, that's a long introduction to what we're going to do in this paper. So we're going to use new machine learning techniques to effectively target who gets home energy reports. And from there, we're going to try to optimize either Eversource's objective function or society's objective function, which I'll get into why those are different in a second. In particular, we're going to leverage some of the new random causal forests that Susan Athey and colleagues have been working on to estimate those different treatment effects across different types of households, and then bring in information about the marginal cost of sending one of these reports to maximize welfare or Eversource's objective function. And then the other thing we're going to do is we're going to compare these causal forests with more traditional techniques of trying to estimate heterogeneous treatment effects. So I would say we're leveraging a bunch of literatures and trying to make a contribution leveraging those two literatures. Definitely, Sam, and I think Sam will agree to this, we are consumers of the new machine learning techniques. We're not producers. So I think as I give this talk, we'll also talk about what we've learned and what are some potential pitfalls in using these techniques. Okay. So as I mentioned, we're going to be focusing our efforts using these causal forests, which is a tree-based approach to estimating average treatment effects. And if you've ever used regression forests or regression trees, it's effectively doing that, where the dependent variable is the treatment effect. I think that's a good intuitive way to think about this. The treatment in this case are going to be home energy reports, which Rob's done great work on this. Lots of people have done work on this. In fact, Meredith Alley discussed this paper recently, and her line was, you know, when I first thought about this paper, I asked myself, do we really need another O-Power paper? Her conclusion was we did, so I'm going to take that conclusion and run with it. And ultimately, the goal is going to be to understand what these gains from targeting are, and as well as also as whether or not the causal forests outperform alternative techniques. Okay, so what do we do more specifically? So we have data on 15 O-Power waves or O-Power experiments. And you'll see these are large experiments. Across not only across 3 states, as well as across a number of years. So when we start thinking about whether the random forests do better than other techniques, we're going to leverage that intertemporal and geographic variation in where these experiments do or are performed. For each, or for a set of waves, we're going to grow a causal forest. That causal forest will give us a prediction for every household of what their expected treatment effect is. And then we're going to combine that with marginal cost data, as well as what is the benefit of a reduction in electricity consumption. And that's going to be where there's going to be a difference from the utilities perspective and society's perspective. And then we're going to show you what I think are, what I show my MBAs actually are the sort of cool marginal benefits look like this, marginal costs look like that. You would maximize welfare here, but O-Power is going to be sending them to a lot more households than what society or the utility would want to. And so that's step 1. A separate but related exercise is then to test the out of sample prediction accuracy of the forests, both in a holdout sample. So think of it as I have this wave with 300,000 customers. I could test how well the forest does by first growing the trees or the forest on 200,000 and then testing how well it does in the set aside sample of 100,000. But because we have different states and different time periods, I could also think about growing a forest for Connecticut and asking how well it does in New Hampshire or Massachusetts, or growing a forest in 2014 and asking how well it does in follow-on years. So that's what we mean by future waves. And then there we'll compare the performance of the causal forest with these other methods. So what do we find? So as many have found, the average treatment effect of an O-Power intervention in our data is about 1%. That's similar to what others have found. If you look at the event study, it sort of grows over time and levels off. But we find significant heterogeneity in the average treatment effect. So those range from anywhere from a bunch of households saving up to 3% to a non-negligible set of households that actually raise their consumption in response to the intervention. And that's been found before. We're not, I find that fascinating, but we're not the first one to find that. That's called the boomerang effect, where effective in the NBER version of the paper, I won't focus on that today, but in the NBER version of the paper, we show that there's a lot of evidence that those that are increasing their consumption in response to this intervention are the ones that you told are doing well. Okay, so you tell somebody they're doing well and they're going to do less well over time. That's not the focus of today's talk. It is hopefully the focus of one of these follow-on experiments with Eversource, where we're going to try to randomize whether you tell people that they're doing well or not. But that, again, I'll leave that for future work. In terms of the strongest predictors of this heterogeneity, there's two, and that's the pre-treatment consumption, so your baseline consumption, and your home value. But we have a lot of other, the forests use a bunch of other demographics and information about the home as well, which I'll get into in a second. And finally, we find large, or second to finally, we find large gains from targeting, especially from society's perspective. And the reason for that is going to be that Eversource's objective is to reduce electricity consumption more than society's perspective. And I'll tell you that, why that is in a second. But from society's perspective, this is a pretty marginal treatment. So there's a large share of households for which you wouldn't want to send because it's not worth the marginal cost of sending it. And now finally, we find that the causal forests do tend to outperform alternative regression-based or lasso-based methods, although we haven't, to be honest, we haven't put standard errors on that statement yet. Okay, all right, a little bit of background. I'll go over this quickly since this is a short seminar, but as I said, the causal forests are building off of regression trees or regression forests, which are effectively partitioning the data into different categories. So it's very different from a regression method. A forest, for those who are not using these methods, is just a collection of trees. And you're taking some combination or linear combination of those trees. Susan Athey and as I mentioned, colleagues, a number of different colleagues have adapted that literature for experiments, where to my intuition, the way to think about it is, as I said earlier, the dependent variable is now the difference, the diff and diff, or the treatment effect. So now you're partitioning treatment effects based on these demographics in a non-linear way. And then the causal forest is growing a bunch of these different trees, and I'll show you what a tree looks like in a second, and then effectively averaging over those trees. Okay, and this is a long literature that I won't get much into, but we know a lot about O-Power. We know a lot about these home energy reports. And again, we're trying to find a niche inside this large literature. If you've never seen a home energy report, and by that I mean you're in the control group, because almost everybody is in an O-Power experiment in the US. This is what a typical home energy report looks like. So it shows your consumption here. Won't let me draw. Your consumption in blue, compared to all of your neighbors, and by all it's typically 100 nearby homes of similar features, and then a selected efficient set of those neighbors as well. So if you were to do better than all of your neighbors but worse than the efficient neighbors, you would often get one happy face. If you were to do better than both the all neighbors and the efficient neighbors, you would get two happy faces. Early on, O-Power put a frowny face in this case, but there was so much backlash to that they got rid of that policy. And very simple intervention. Often page 2 includes potential ways to save electricity and so on. I think most, and there's been nice work that suggests that there's also long-term effects of these, as well as sort of ratcheting. If you stopped giving these, you sort of migrate to where you used to be, but if you started again, you would go down and so on. Okay, so Eversource's home energy report program. So Eversource is the distribution company in 3 states, in Connecticut, Massachusetts, and New Hampshire. In some locations, they're both the gas and electric utility. In some, they're just one. We're going to be leveraging their electricity home energy reports. And the typical experiment here has about 900,000 households. Usually about 80% are treated and 20% are in the control group. And Eversource doesn't have smart meters, so all we have in terms of electricity consumption is monthly electricity consumption during, before and during the experiments. What we also got from Eversource was Experian data. So for every household, we have a ton of information, and I'll show you a table in a second. But these are things like income, children, we know the size of the house, we know the value of the house. There's even a green score in these data, and that's what we're going to be feeding the forest. Okay, so we're going to be allowing the causal forest to partition households based on those Experian data. And then at the end of the day, we'll have estimates of average treatment effects for a given household type. Before I get to that, I'm going to show you just what the average treatment effect looks like, as well as an event study, just to show you that these interventions matter. So this is the average treatment effect across the 15 waves plus all the waves pooled. So this is in percentage terms. For most of the results, I'm going to show you in kilowatt hour terms, but this is in percentage terms. They're fairly similar. So we find that it saves about 1%. But you see there's a fair bit of heterogeneity across the different waves. Whether or not, you know, that correlates with which state it's in or which location doesn't seem to correlate well with that. I'll highlight one, which is the Connecticut low income wave, which is started in February 2016. So the nomenclature here is Connecticut, February 2016, low income. That was just sent to low income households. And there you see that the average treatment effect seems to be pretty small. So one thing, the one way O-Power does target is O-Power usually has a threshold for which anybody below that threshold in terms of monthly consumption, they won't touch. And they just send it to large customers. So that low income result might be driving that, or it might be an income effect. But what the forest will try to partial those two effects out.
Chris, can I just,
yep.
Just ask a quick question about this? So just by like eyeballing these, it seems to be a little bit consistent with Hunt Olcott's 2015 paper, where they go after like the low hanging fruit first. They seem to get the larger effects early on, and then as they look for more samples, which are usually using less energy, it's hard to get those effects. So maybe you can come on to this when you talk more about the machine learning approach, but it'd be good to get a sense of like how different are these samples on the covariates, and whether that's going to help you or hinder you when you're thinking about the machine learning algorithm.
Yeah.
And then the related question to that, so I'll just ask them to both together,
sure.
And then you can respond, is like, from what I can tell, O-Power seems to be like changing the treatment over time, right? So they kind of do all the experiments and try to figure out what is the optimal, not just like the social norm, but what tips, what subsidies, or what rebates for technologies are put on the HER. And so how do you factor in sort of the change in treatment over time into the algorithm?
Yeah, so the two great questions. So so to be honest, like in the forests, we haven't really fed it time, right? So we haven't let it partition the average treatment effects over time. So that's something that we might want to try. But one of the horse races, we call them, that we're going to do is grow the forest using only 2014 waves, and then see how well it does in follow-on waves, and then compare the forest with other techniques. So we'll sort of be doing what you suggested, or at least one test of what you suggested in the future. But you're right about if I eyeball it, the treatment effects do seem to be larger earlier on in the sample. In terms of them changing their treatments, so at least according to Eversource, and this is where Sam could correct me if he has different information, they haven't felt like they've been doing much in terms of the home energy reports, at least in this sample. So I think a lot of those changes have been happening later than maybe these. And part of it is in response to Hunt's result, right? Which is they're not squeezing as much out of the turnip as they used to. So they're trying to be more proactive in changing that. So we're going to be treating the home energy report as a constant treatment effect, or a treatment at least.
Awesome.
Okay, so here's what the event study looks like. So you could see that treatment effects tend to grow over time. If I squint, I might say that they level off. Although if I squint it a different way, I might say that they seem to be still growing. But we stopped this at 36 months post treatment. And I will say, in full disclosure, Eversource has since stopped using O-Power and is sort of partially leaning on Sam and I and their own internal expertise to develop their own home energy reports. And that's where we won't be getting much more O-Power data from them, but we will be able to hopefully be able to run our own experiments. Okay, so causal force. So we're going to be using an off-the-shelf package developed by Athi Tibshirani and Wagner. What we're going to be doing here is growing 10,000 trees. And like I said, I'm going to show you a tree in a second, where this is, if you don't have any experience with this, I think they're pretty cool. So the way that a tree works, intuitively, is imagine just trying to partition average height, let's say, and you have a bunch of characteristics on people, and you're trying to have an average height for different types of people. What a tree does at the very beginning is it splits on some characteristic. So that might be male, and maybe you only fed it gender and weight or something like that. So it's going to split anywhere inside of, let's say it wanted to split on weight, anywhere inside the continuous weight distribution into two groups initially, right? So that's your first branch. And the way it's going to split is in a way to either maximize predictive power of the two averages that it's going to have, or another way that is equivalent in many cases is to maximize heterogeneity. So it's going to now have two average heights, one for people above this weight and one for people below this weight. Okay. And like I said, the way it split that was to minimize forecast error. Then at the end of each of these branches, it's going to split again. And over here, it might split on weight again, or now it might split on gender. Over here, it can split on whatever it wants. And it's sequential in that way, so that each time it's minimizing forecast error given that split. Okay, it's not forward looking. So it doesn't know it's going to split on gender next when it splits on weight the first time, right? And then, so after it's done splitting, you now have for all these different categories, an average height for each of those groups. What stops it just from splitting so that it has one person in each group? You have to feed it a penalty for a split, or you can feed it a minimum leaf size at the end so that you can only have at least, or you have to have at least 5 people in each of the final leaves. So a forest is just going to grow a bunch of those. What's different with the forest is you're grabbing a different sample, and you're also typically, although you don't have to do that, only feeding it a subset of the X's that it can split on. And that's going to uncorrelate the trees in certain ways. And then at the end, you have 10,000 trees, and you can calculate an average height, in my example, for a given person, given all of the splits in all of the trees, or all of the trees, okay? So the causal forest, the one thing that I didn't mention in the causal, or the causal honest forest, is that when it goes to calculate the average treatment effects, it doesn't use the data that it used to split on. It uses a holdout sample data, so that's what makes it honest, in the sense that you're not over splitting or overfitting for your sample. So you could think of that as similar to a cross-validation sample. Okay, so here's what a forest or a tree looks like, sorry. So this is an actual tree in our data. So here you can see the first split was on home value. So to the left are home values below that 563,000, to the right above. And then to the left, it splits on home value again. To the right, it splits on income, and so on and so forth. So you could sort of trace the tree as it continues to split. We have a minimum leaf size in our setup. So at the end of it, that's what stops it from splitting. And then each of these leaves, the final termination nodes, you'll see the average treatment effect. So I'll go over here. The average treatment effect of that one is a savings of 1.38%. Then it has the total number of people in there as well. So the greener it is, the larger the savings. So you find some households that are saving over 3%, some households that are saving around 1%. And then if you searched around here, you would probably find a household for which or a group of households for which the average treatment effect was positive. Okay, so in here as well. So we're growing these 10,000 trees, that creates the forest. And how you come up, just a technical detail, how you get the average treatment effect for a given household, you calculate the number of times I'm in a leaf with Rob, and the number of times I'm in a leaf with Sam, and so on and so forth. And then I take the weighted average of their average treatment effects. That's my average treatment effect. Okay. All right. Now there's several, again, as practitioners of these methods, I'll just warn you, there's lots of nuisance parameters associated with these. And we probably have a 50-page appendix just sort of working our way down of how we chose these different nuisance parameters. So, you have to choose, what share of the X's you're going to feed each tree, how large the sample is, the minimum node size. There's also an imbalance limit and a penalty, right? So as you work your way down these forests or these branches, remember, O-Power typically treats 80% of the sample. So you can run out of controlled households very quickly, right? So that's what the balance sample, the balance on how many treatment, how many control samples you have in, or households you have in each leaf. So, we found that it can be sensitive to that. What we tended to try to do is choose these nuisance parameters to maximize forecasting ability. That's one way to choose these tuning parameters. Others are, some suggest that like the minimum node size, you choose something that's small but not terrible, right? Terribly small, right? So you look at how forecasting ability looks over the minimum node size, and you look for a flat area, and you pick at the end of the flat area or at the beginning of the flat area. A couple other things that I'll mention, what we're feeding the forest, because we have panel data. So we have a bunch of months before treatment, a bunch of months after the treatment. You can't feed it, at least as of now, panel data. So what we feed it is an average pre-consumption and an average post-consumption, where we residualize consumption using a regression of monthly consumption on the characteristics and wave fixed effects. So we're feeding it a residualized consumption and treatment.
Okay. Just a quick question. Sorry, Chris, just a quick question. How does measurement error of your covariates come into this? So, my experience of working with utility data is the consumption data is awesome. Like it's fantastic, but the other variables can be a bit sketchy, and especially like home value, square foot, what technologies they have in the home. If they do have that, it's normally like a snapshot in time. So can you sort of talk a bit more about sort of the panel nature of your Y variable, which is awesome, with like the less panel data that you have on the X's?
Yeah, that's a great. So my intuition, and there might be a paper on this using regression forests, but maybe not causal forests. I haven't seen anything on causal forests along those lines, but I would imagine somebody has thought about measurement error on the X's in regression forest. My intuition, having just played around with these, is the more measurement error in the X's, the less likely it's going to split on it, right? Because it's going to be useless information. So if you just take the limit of measurement error, you're feeding it a random variable, it's not going to ever want to split on that white noise variable. So that's my guess. So I would just think that it would degrade the ability to split. And I don't know. My next question is, does that create bias? I'm not sure. I haven't thought about that, but the fact that it's not splitting on that makes me suggest that it. And remember, these are forecasting models and not regression models from that perspective. So I don't even know how I would define bias in that sense.
Mm-hmm. Yeah. It's just like interesting because you mentioned up front that home value is a good predictor. And you can imagine as you increase your home value, you probably maybe like use more energy. And so you might flip from being like a conserver to a non-conserver over time. So it's just really interesting to think about those issues.
So I'm not paying attention to Q&A, but I saw like what's the criteria used. So that's where there's always a cross-validation sample or the honest sample. So if you just grow a tree, it's going to choose the parameters so that it maximizes forecast or minimizes forecasting error. So that tends to be the criteria for how you can tune these parameters, right? So you can pick the optimal set of parameters for which the forest does the best in predicting average treatment effects.
Got it. And then there's a question by Sally Sadoff, which is, do continuous variables like the energy, are they treated differently than the binary variables? And she said when she's used similar methods, they give more weight to continuous. Yeah, go ahead.
So they're not treated differently, and that's why I think they lead to they get more weight in the forest. Because remember, the forest, like think about pre-baseline consumption, it can cut anywhere in that whole distribution of baseline consumption, right? Whereas obviously a dummy variable only has this group or this group. So it can optimize where it cuts, right? So that's where continuous variables sort of have an extra degree of freedom from the forest perspective in reducing forecasting error. All right, so let me show you our results. So these are probability distributions of the average treatment effects. Okay, so the left panel is across all years in the data, and then the right panel splits it so we grow a different forest for the first year after treatment, second year, and third year. The black one is useful, but I like to focus on the different years. because it shows some intuitive patterns. So if you look at the first year here, what you find is a big mode of saving around 10 kilowatt hours per month of consumption. And that's a little bit less than 1%, okay? And then if you squint, you see another mode where there's sort of another group of households that seem to save more than that. And then not surprisingly, you see a mode at 0, right? And that to me are the households that never open the stupid thing, right? So they never even see it. So how are they going to respond? Or it's a households that open it and just ignore it. And then when you go to year 2, which is the lighter gray, now you start to see the distribution stretch a little, right? So you start to see more people, more households responding more. So households sort of separating themselves out in responding. And then you still see, they're not technically modes, but you see sort of a bump at 0. And now you start to see another group for which they seem to increase their consumption in response to these. And again, I often stress this because this isn't like, so I grew up in an IO world where we estimate random coefficients. This isn't a random coefficient in that sense, in the sense that I have an average beta and then I have a distribution around that beta. What's different here is I know exactly who these households are, right? These households have this income, this home value, this many kids, and so on and so forth. Whereas in the BLP world of random coefficients, you just know there's randomness out there. You can sort of guess at it using conditional expectations. But in this case, I can tell Eversource, and in fact, we do tell Eversource, it's these types of households save this, these types of households save this, and so on and so forth. Okay, and then when we get to year 3, you see this mode even moving further, and then you see even more stretching out of this. Okay, so that's what comes out of these models. This is useful in the sense that it tells you what the forest is using when it's splitting at the different split levels, right? So this is the first split right here. And the first split is almost always baseline consumption, right? So O-Power has it right from that perspective. O-Power just uses baseline consumption to target, right? And that's definitely what they should be using if they can only use one. And remember, the individual tree doesn't always get to use baseline consumption. This is the percentage when it gets to use it. So 90% of the time, if it's allowed to use baseline consumption, it will in the first split. And even the second split is likely to be baseline consumption, and the third. And then after that, it starts to use these other categories. Square footage comes in, age of the head of household, home value, income, and when the year was built, when the house was built. Okay, so that's what it's using. And I'll come back to some graphs in a second. How well does it do out of sample? So Davis and Heller have a nice AER papers and proceedings where they use this technique on a summer job program. They suggest the following test, which is you grow your tree on half of your sample, you predict who's going to be in the 4 quartiles in terms of treatment effects. You use those predictions in your cross-validation sample, and you estimate the treatment effects in that holdout sample. So you could see this is the sample you grew the tree. This is the sample, the holdout sample, and the cross-validation sample. It seems to do a really good job at predicting average treatment effects in that out-of-sample case. We're going to come back to more tests like this in a second. In terms of, so the one bad thing about using these forests is, the nice thing about a regression model is you have a beta, and you could say as incomes go up, average treatment effects go up, or something like this. Remember, this is just splitting into a bunch of different groups, so nothing has to be continuous or monotonic or anything with respect to these variables. With that said, this is a scatter plot of the average treatment effect for every household in our data over baseline consumption. So you can see that baseline consumption, as it grows, the average treatment effect gets more negative. Okay, so this is O power targeting, saying, look, it doesn't make sense to send it to the people to the left of this line. We're just going to send it to the people to the right of this line. So that is fairly monotonic. If you look at home value, though, it's basically flat through home value, but it's still using home value a lot. I don't know if you remember that characteristics. That was the second most frequently used X variable. This is a huge figure. That's why it's taken a while to load. But so even though it's using it a lot to split, there's no monotonicities. What it's finding is little pockets of home value conditional on the splits above it that seem to predict average treatment effect. And this is where a regression-based method is going to have a really hard time finding those different pockets. With enough interactions, you can do it, but then you run the risk of over parameterizing things. All right, so now let's get into some actual economics. So what we're going to do now is we're going to take those distributions of average treatment effects. We're going to effectively sort them from largest to smallest, and that's going to be the benefit of sending these home energy reports to the different households. That's going to be the marginal benefit curve, and then I'm going to have some estimates of marginal cost. And we're in, just like in Econ 1, we're going to say, well, what would happen if we stopped where marginal benefits equaled marginal cost instead of keep sending them to all households in the data. My iPad's chugging along. The resolution should go up pretty soon. Okay, so home energy reports are not free. I'll have a marginal cost estimate in a second, but I do want to talk about Eversource's objectives here, right? So Eversource or utilities objectives for, why do they want to reduce electricity consumption at all? To a first order, it's often because the regulators are telling them to. But also if you're what's called a distribution company like Eversource, so Eversource effectively owns no generation, then from their perspective, reducing electricity consumption is either they're indifferent to it, if not, they're fine with it, right? So they're not benefiting from any generation. They benefit from the regulator counts up how much money they spend on wires, calculates a rate of return, and then allows them to earn that rate of return. So Eversource has no problem reducing consumption, especially if it's not going to reduce how much wires they have. In the short run, it's definitely not. And in the long run, it may not either. So from Eversource's perspective, one might think, or the regulator's perspective for sure, that their objective or the value of these kilowatt hour reductions is the retail price of the kilowatt hour reductions. Society, though, cares about the marginal cost of electricity. And a lot of what goes into the retail price of electricity is paying the fixed costs of those wires. So when we think about society's objective, we're going to use the average wholesale price of electricity as the marginal benefit from a kilowatt hour reduction. And that's going to be much smaller than the retail rate. And that's why it's going to be, Eversource is going to have an incentive to send these reports out to way more people than what society would want to send them to. Okay, so what marginal cost number are we going to use? So here's where we have good data on what OPower charges Eversource. We don't know, how much of that is a markup, how much of that is, other non-marginal components. So we're just going to use effectively the price that OPower charges Eversource for one of these home energy reports. And that's an average of about $7 per household per year for these reports. Okay, how am I doing on time? All right, oh no. So now we're having issues here. This is supposed to be a graph. Shoot. This is actually the killer graph, so I don't want to lose this. Rob, you want to ask me a question while I look up something?
Yeah, sure. So hopefully you'll talk a bit more about sort of the outer sample predictions? Like how well
Yeah.
does the model do outer sample?
Yeah, let's see if it comes up here and it's just, okay. So I am gonna get to that in a second. Let me just get to this, which I find, so this is the marginal benefits versus marginal costs, right? This is from Eversource's perspective. So you could see, and we split it up by year 1, year 2, and year 3. So in year 1, remember the average treatment effects are small, they're growing over time. So the marginal benefit of sending this is lower. So the black line is year 1. They send it to all the people in our data. What this is suggesting is in year 1, they should only send it to 75% of the households, right? Because at above 75, the marginal benefit is below marginal cost. We can calculate the maximized welfare in year 1 is 6.3 million. The deadweight loss to sending it to everyone is 824,000, right? About 13% of the maximized welfare. So the maximized welfare over time is growing because the average treatment effects are growing, but so is the deadweight loss from sending it to everyone. Because remember that mode at 0 was moving to the right, and now you have people who are actually consuming more electricity and making things worse. So from Eversource's perspective, the deadweight loss as a share of maximized welfare is fairly constant. It's still, though, small. I would say 10%, 11% is small relative to the total welfare. If you go to societies, from society's perspective, though, now all of a sudden deadweight loss can be larger than the maximized welfare, right? Because again, the benefits of sending these reports are smaller because you're using a smaller price of electricity. Now at the end of in year 3, the deadweight loss is still 42% of the maximized welfare. So actually that's the benefit of targeting here. That what you would do is stop sending it to now about 30% of the households, larger, but the deadweight loss is also larger. I'll quickly get to what Rob was asking, but the one other thing I wanted to point to is you might be thinking, well, it's really hard to figure out who you should send it to if you don't have any data to grow a tree. Well, what we show is that if you just send it to everyone in year 1, grew the tree with just year 1, that's enough information. From that, so the off diagonals are the mistakes from not growing the tree in year 2, right? So if you just grow the tree using year 1 data, it's that do not send in year 1 and do not send in year 2 group is 119,000. The off diagonals are pretty small from that perspective. And even in year 3, if I just grew the tree in year 1, I would get it pretty much right as well. So from Eversource's perspective, they can maybe waste that deadweight loss in year 1, but that'll allow them to eliminate the deadweight loss in year 2 and 3. Okay.
Sorry, Chris, just a quick question on these figures, on the deadweight loss. So from the objectives of the utility or the Public Utilities Commission, what happens if like the people on the right-hand side below the cutoff actually enjoy receiving these reports, and they're willing to pay, more than $7 a year to receive a message telling them how great they are?
I'm glad you asked that, because what I didn't mention is we do that from society's perspective. So we take the Alcott-Kessler results and then we add on a willingness to pay to the marginal benefit of sending them. And that's the difference between panel C and panel B. What we haven't done it is from Eversource's perspective, but from Eversource's perspective, you should almost send it like what we're trying to do is stack the deck in favor of sending it to more people from society's perspective using their results. So it doesn't really change the numbers too much, but that's in there. Yeah.
Got it. Yeah. Because I always hear about like they care about JD Powell scores of like customer satisfaction, and that's the important part. But I don't know whether willingness to pay captures all of that, but yeah.
I'll say we've grown trees on satisfaction because Eversource has given it. And from Eversource's perspective, they don't like these home energy reports because the ones that enjoy getting them never call them and tell them they enjoy getting them. The ones that hate them call them constantly about that. So that's one thing that that's an added concern from Eversource's perspective. Okay, so let's do some horse races. So, before Susan Athey did all this stuff, how I would have went about doing this was probably running some regression, interacting the treatment with the X's, and then estimating heterogeneity that way. Maybe 2 years ago, I would have used Lasso because I started using Lasso about 2 years ago. So what we're going to do is test or compare the forecasting ability of the forest with a bunch of different regressions as well as Lasso. And it turns out Lasso, when you do Lasso, it never chooses any of the treatments. So that's not even going to be in the results. But we did try to compare it to Lasso. So what are the 4 regressions we're going to do? So we're going to do a fully interactive over-parameterized regression, where second order Taylor series expansion in the X's. Then we're going to do what we call the parsimonious regression, which is just the linear and squared terms, then just the linear terms, and then something that's similar to O-power where we just use pre-mean in the regression. Okay, and that'll end up being just a cutoff above and below. Okay, so the first horse race is we're going to use the same types of households in both growing the forest and running the regressions, then comparing the out of sample forecast. So here we're going to take all 15 waves, randomly select half of the sample, grow the forest / run the regressions, and then forecast for the cross-validation sample. And I'm going to show you net benefits of sending these reports to these different households. We're going to do 3 selection criteria. We're going to have the method pick the 10% most highest benefit households, then the 25% highest benefit households, and then we're going to have them do the full optimization of marginal benefits equal marginal cost. Okay, and then I'm going to show you the net benefits of doing that. The second horse race is going to be, and I've sort of mentioned this, grow all the trees, run the regressions on the 2014 waves, and then use those results to predict benefits in the 2014 waves. Same 3 groups, top 10%, 25%, and marginal benefits greater than marginal costs. There's one thing that I'll highlight, and we have a long discussion in the paper. The way we're going to estimate actual treatment effects is in that holdout sample, we're just going to do a simple diff and diff for that group to get the average treatment effects for that group. We're going to use the same residualized data that we feed to the forest. We've also estimated those treatment effects with inverse probability weighting, and we tend to find different treatment effects, actual treatment effects across those 2 methods. There's a whole discussion in the paper why we still use the residualized one. My argument is that's what we feed the forest, and it would be unfair to feed the forest the residualized data and ask how well it does in predicting a different regression. But that's, again, offline, happy to talk about that. Okay, so those are the different waves. When we do the time, the one thing I'll highlight is the early waves look a lot different than the later waves. So we're really stacking the deck against all these methods. So the fact that they do well at all is pretty good. And here's, just to show you the balance between the 2014 wave is group 1 and all the follow on is group 2. So 2014 had lower home values, higher income, but basically on all these X's, they're all different. So again, this is a good test for these methods, I would argue. Okay, so this is within group top 10%, right? So we're going to have all these methods say, you tell me who are the biggest savers, 10% savers, and then I'm going to send it to them, and then I'm going to estimate net benefits above the $7 marginal cost. So you can see here, the forest outperforms all of them, about a 20% increase better net benefits relative to a regression that just uses the pre-mean. The other thing that's interesting here is notice that the more complicated the regression, the worse it does, right? So the fully interactive model does worse, parsimonious does it. And then when we just feed it one variable, it does better than the linear model. Okay, so the forest is doing its job in limiting its parameterization. When we look at the top 25%, the regressions start to do a little bit equal to the forest, and in fact, the linear model is a little bit better than the forest. The forest is still, you know, outperforming the fully interacted and the parsimonious model. So here, I would say, you know, certainly if we had standard errors here, it would be sort of a wash between the forest and those simple regression models. When we ask it to do net benefits, the forest does better again. Okay, now it's about 10% better than the pre-mean regression. What O-Power does, which is sending it to everyone, does the worst, right? So all methods are able to eliminate, on average, some useful elimination or some targeting relative to O-Power. So from this perspective, I would say, you know, the forest sort of wins here, not by a large amount. So now we're going to go, oh, man. When we look, and this is probably what Rob wanted. When we look on the follow-on, the follow-on years, the forest outperforms all the methods there as well. So the conclusion from the horse race, I would say, is that the forest does as well, if not better, than every method in every case. So from that perspective, this routine seems to be a good way to use experiments to target who to treat. Okay, so and that's really my wrap up, Rob.
Awesome, thanks, Chris. That's really interesting how like the pre-consumption variable is up there for most of the way in the prediction.
Right.
That's really is fascinating. So does that make you think that that you would want to capture more sort of unobserved variables from these households? Like, could we somehow use the Olcott and Kessler distribution of like the willingness to pay as like their preference for it, and put that, like impute that for the population and use that as an unobservable about whether they like it or not?
Yeah, definitely, in the sense that, and I don't know whether you do that pre-forest building and just adjust the average treatment effect to include the willingness to pay for every household, right? So like if you had a willingness to pay for every household, you know, we feed the forest the change in consumption, but you could feed the forest the net benefits of sending the report, right? Mm-hmm. And then adjust that using the willingness to pay, and then just say, okay, grow the forest to tell me which types of households have positive net benefits and negative net benefits, and then you're done.
Mm-hmm. Absolutely. It's also this is a really good example where, you know, you have really large sample experiments and multiple experiments in different locations. So I suspect other people are going to use this as a template to understand or to practically implement the machine learning algorithms with a large randomized controlled trials. And I'm just sort of, you know, wondering what's sort of the next extension for you on this area? Like, what would you like to have that you didn't have that you think would allow you to have a better prediction algorithm?
Yeah, I think what I want to investigate more, which, remember, so we did the 2014 for the follow-on. What I'd really like to understand, and we can do this, we just haven't done it, is the geography effects, right? So, you know, if I grow a forest using Connecticut data, how well does that predict Massachusetts data? And obviously that's going to be context dependent, but how stable are these forests, right? Because that's basically asking that question, which is how stable are these cuts as we move to a different population, or a different sample of the population. And these forests are designed just to forecast. They don't care about the cuts, and they don't interpret the cuts like I often want to interpret the cuts, right, as an economist. And so that's the one thing that I'd like to convince myself of. Yeah.
Got it. Okay, I think we're just over the hour. Thank you, Chris, for this really interesting and informative talk. Really appreciate your time and your wisdom and expertise in this area. It is really, really fascinating research. Thank you also to Sam for answering all the questions in the Q&A. That was really helpful. So thanks, Chris. Thank you everyone for joining. Next week we'll have Gautam Rao from Harvard talking about some policy experiments. But we'll see you all next week. Thanks again, Chris, and thanks, Sam.
All right. Thanks for having us.
Thanks, everyone. Bye.